Hi everyone. In the previous video, I introduced flux and I talked about the change in flux that would cause an induced current inside a loop. Now we want to talk about the equations behind the change in flux. So if you remember, we mentioned flux. Flux, it is equal to phi equals B A cos theta. If you either change the magnetic field or you change the area or you change the angle between the area and the magnetic field, flux would change, and the change in flux would lead into an induced voltage. So if the magnetic field changes by moving a magnet towards a loop or moving it away from the loop, then you're changing flux. Therefore, you have a delta phi, the change in flux over time, equals a delta B over delta T times the area times cos theta. Area and cos theta are not changing, only the magnetic field changes. You could do this by moving a magnet towards a loop or moving it away from the loop. Or what you could do, you could have magnetic field lines going into the page, and you could have a rectangular loop in here, and you could increase or decrease the amount of the magnetic field. You could do that. You could increase or decrease the amount of the magnetic field. In that case, you have a delta B, delta T, delta B over delta T, and you have the same area. Area is not changing, and times cos theta, that would change the flux. The change in flux can create an induced voltage. The induced voltage is shown by delta V, and it is equal to minus n. N is the number of loops. If you have one loop, n is 1 times delta phi over delta t. So you could grab this equation and put it in here for delta phi over delta t. The minus sign means that the induced magnetic field created by the loop would always oppose the increase or the decrease of the actual magnetic field. That's what this minus means. If you want, you don't need to use that minus sign in order to calculate the induced voltage. You can just use n delta phi over delta t. If you want to calculate induced current will be delta V over the resistance. Another way to change the flux would be, for example, you're having some magnetic field. They're going into the page. They're represented by B. And you have a loop trying to enter this magnetic field with a velocity of V. If I take the width of this loop as L, remembering L should be perpendicular to the velocity. In that case, you're changing the area. More of the area is exposed to the magnetic field. It's like you're actually increasing the field. By increasing the field, the loop would create an induced magnetic field coming out of the page to oppose the increase of the actual magnetic field. Now I want you to use your right hand and put your thumb in the direction of B induced. Curling your forefingers should show the direction of the induced current. If that is the case, you guys see that induced current will be going counterclockwise. So you have an induced current that would be going counterclockwise. If you want to find the equation for the induced voltage, delta V, it's equal to B A, actually it's equal to B cos theta times delta A over delta T, which we really don't use this equation. Just wanted to show you that the area is changing, but the actual equation that you will be using in the exam, I'm pretty sure you'll be doing that. It is equal to BLV. B is the magnetic field, L is the width of the loop that is entering the field, and V is the velocity of the loop. You could put a minus sign here, or if you want to calculate the magnitude of the induced voltage, you don't have to put the minus sign in the equation. If you have delta V, again, induced current is equal to delta V over R. So if you have a rectangular loop entering the magnetic field or exiting the magnetic field, this is the equation that you're going to use to find the induced voltage. Remembering that when you're entering the field, your B induced wants to oppose the increase of B, so it will be in the opposite direction. But when the loop is exiting the magnetic field is actually decreasing, so B induced would be going into the page. So your current will be going clockwise. We talk about that in the exam prep session. So I want you to remember, when you have a loop entering or exiting the field, more of the area is exposed to the magnetic field when it's entering the field, and the equation that you need to use is going to be BLV. Make sure you're very comfortable with the direction of the induced current.